Hey, APCal class, we're going to start in a whole new unit, and really this is taking us into basically the other half of calculus, which is the integration process. You know, in any operations in mathematics, you have an operation and then its inverse operation: addition, subtraction, multiplication, division, squaring something, square rooting. So we've been studying derivatives, and now we're going to get into, and this is going to be a very large portion of this course. Really, the remainder of it is integration, and we're going to start with the very kind of the origins of what it really means. And in this section, it really refers to area under a curve, basically, or under a function. And you know, when we talked about derivatives, we said that that was referring to instantaneous rate of change. So it was the slope of a curve at any specific c value or x coordinate on that curve. And so this, you know, really the main function of integration is going to be finding an area under a curve. Now we're going to start with we're going to break it down to this, kind of what we did with derivatives when we started. There's a definition, and it involves the limit, finding a limit of a sum. Okay, and so there is going to be some technical mathematical notations that involve some summation properties that you probably aren't super familiar with. So we're going to take a look at it. It's not going to be, like a gigantic portion of this course, but it is something that we do need to introduce. As far as the AP exam, there might be a question or two that throws a little bit of this in there, but it's, like I said, it's not a real big part of it. But so with that in mind, we are going to just kind of review, or maybe for the first time see some of these properties that involve this. It looks like a giant E, but it means the summation of some numbers from, a bottom number, which is where you're starting from, the lower bound, up to the upper number, which is your upper bound. And a lot of times they use this letter I as your counter. So I is like your counter. So for example, in this one, and it's called sigma notation. This is the Greek letter sigma. So with these sigma notations, basically what this is saying, it's saying, hey, if I would add up all of the numbers from 1 to 6 when I plug them into just this function I, what would I get? And so, that's pretty easy to do. So all this is really asking you to do is say, okay, if it's just I, then it's my first term is 1, my second term is 2, and I just add up all the numbers from 1 to 6. And that's all I have to do to get my solution to that one. So if I were to do that, 1 plus 2 plus 3 plus 4 plus 5 plus 6, you would see that you were going to get 21 for that value. Okay. Now, in the next one, same idea. We're adding up all the numbers from 3 to 12, but the function that we're kind of putting them into is squaring, right? So it's j squared. So we're going to square each of these numbers and then add them, all of the ones from 3 to 12, okay? So just the kind of, these examples, just getting used to what does that sigma notation mean. So we'd have 3 squared plus 4 squared plus 5 squared all the way up to 12 squared. Okay, now you're going to use a calculator to probably do that, but if you were to type all that stuff into your calculator, you're going to see that adds up to 645. Okay, but just, understanding what is this asking me to do. So you get your lower bound to your upper bound, and you're adding each of the terms up that when you plug in, each of those numbers into whatever this function is, you're just finding the sum of those. So it's a summation of all of those values from the lower to the upper. Okay. Now, sometimes these expressions get a little more complicated than just I or I squared. They're using j, I guess, in this one. So there are there's some properties you can use to calculate the values without having to go through and add them all by hand, because that gets real tedious, especially if you have a lot of numbers from your upper bound, from your lower to your upper bound. Okay, so there are some formulas here. Are you going to have to memorize them? A couple of them for the quiz and test. I'll be more specific about what you really need to memorize as we get closer to that point. So these were some more of the properties here, formulas down below, but kind of like this property is used a lot. And what we're going to notice is that once we move into actual integration, and the integration symbol looks different than this, but a lot of these properties are exactly the same as your integration properties. So if there's a constant multiplied by whatever your function is here, that constant can get pulled out in front. If you're adding two different functions, you can do the summation of them separately, just like you would do with integration, as we're going to see later. Subtracting, same idea. Okay, so as far as these formulas here, maybe we just have a constant number, like we're, if our function is just a constant and we're going from 1 to whatever this number is up here, which they're calling n, then all we do is take our constant times that n. Okay. If we have, just like what we had in the first example, if it's just I. So in other words, if it's just increasing by, I every time by 1. Okay, so we're going from 1 to 6. So this basically just means add all the numbers from 1 to 6 because it's just I. We're not changing them. We're not doing anything with them. Okay, so here's the formula for that one. There's kind of a backstory on this formula that I've heard in college and some other grad class I've taken. But so this Carl Friedrich Gauss, he was a child prodigy in mathematics, and apparently the story goes that he was much smarter than his teacher even at a really early age, and so his teacher would get very annoyed with him because he would start causing distractions and trouble, and so she told him to go over to the corner and add up all the numbers from 1 to 100, and when you're done you can come back and join the class again. So he sat down, and within just a minute or two he had the correct answer, and she just couldn't figure out how he figured that out so quickly, and so teacher had him explain to the class how he did it, and he just said, well, I was just adding them, and so I started 1 plus 2 plus 3, but then I thought, well, I don't need to do all of that because that's just going to continue in this way, and at the end I'm going to be adding up to 100, and so I started counting backwards this way, and notice that, well, it's always 101, 101, 3 plus 98, 101, and it's going to be that since I split them in half and took, if I go up to 50 this way and then backwards from 50 to 100 this way, I'm always going to get 101, but that'll be 50 times that happens, right? So it's just going to be 50 times 101. And so that thinking was used to kind of develop this formula. If I'm adding all the numbers from, so for example, with the problem Freddie Gauss was asked to do, from 1 to 100, and we would just say I for that because we're not changing them, we're just adding those specific numbers. The idea here, so this 50 comes from taking 100 divided by 2, so that's that n divided by 2, and then since there were 100 numbers, the 100 plus 1 gives you the 101. So it was like the n divided by 2 is the 50, and then n plus 1 right here would give you that 101. And so that formula is kind of developed from just his brain of thinking how I could do that real quickly. And so kind of an interesting one there. So I kind of, this one I remember because I can kind of think of this problem that I've seen a few times. But anyway, there are some more complicated ones then that probably are a little tougher to memorize. But like I said, there isn't going to be a lot of stress on memorizing these, but they will be used on a few of these, these first section problems. Okay. So for example here, if we were going to evaluate this summation, we'd use the properties of saying we can take, each of these pieces individually and find the summation from 1 to 25 of those, and then apply whatever formulas that we would need to use from up here. And so since this first one, it was an I squared, that has a little more complicated formula. N times n plus 1 times 2n plus 1 all over 6. And so if n meaning it's the upper bound number, it's at 25, okay? So for this one, I'd have 25, and then the next one would be 25 plus 1, so that would be times 26, because one more. And then the next one would be 2 times 25 plus 1, so 2 times 25 is 50 plus 1, that'd be 51. So those would be the three numbers that I would multiply in the numerator, and then I'd have to divide that by 6. Okay, so that's this formula for this piece, the I squared piece. Okay, so in that I can just type into my calculator and come up with that number right there. and then I'm going to subtract, and then the next formula is this one that's just I, which we saw, that's what I kind of explained here. So if we're just going 0 to 25 on that one, so we would have, if I'm using this formula, 25 times 26 and divide that by 2, 25 times 26 divided by 2, and then I would add to that. Now when I just have a constant like this, that's just this formula, it really just means 4 plus 4 plus 4. You do that 25 times, so obviously it's just 4 times 25 for that part of it. Okay, so that's, just using these summation formulas, and I can calculate that out without too much problem, I think. Okay, I'm not going to type those in a calculator for you, but that's how you break that down. I mean, you can do that. Okay, so next piece here, it says, okay, use sigma notation to rewrite each of the following. So kind of what we're looking for here is, we want to see what's the pattern here, what numbers are staying the same and what are changing. And the ones that are changing, that's, that's kind of what you're looking for as far as what your I is going to be represented with. So if I've always got a 5 in the numerator, then, I'm going to leave that in my formula. So I'm going to have a summation. And maybe you can see if I started with 1 plus 1 here and I ended with 1 plus 15, then I'm going from 1 to 15 on my counter is going to go from 1 to 15. Okay, and then if my numerator is always 5, I would have 5 in the numerator, and in the denominator I'd have 1 that's always in every one of these, 1 plus 1, 1 plus 2. So that's going to stay the same. But then what's changing, I'm going to call that I, because I is what's changing from 1 to 15. So in the first term, it would be 5 over 1 plus 1. On the second term, it would be 5 over 1 plus 2, and so on. So this is my sigma notation to represent this series that I have right here. Okay, whoops. Okay, so this would be my solution to that one. All right. All right, the next example is just a little bit more to it. But what I want you to notice, as you're looking, just look for the things that stay the same and then the things that are changing. Okay, so as I go from this first term to the next one, where the addition signs are changing them, I just want to look for what are the things that are different. And I can see it's 1 minus something in every one of these. So that's going to stay in my formula. The 2 over n, I can see that that's being multiplied to each one of these terms, all the way to the end of it. Okay, and so that piece, when you see that there's a multiplier in there, that's where you can use this property from above that says, if I have a constant multiplier on all my terms, that can just get pulled out in front. And so in this one, if I see that there's a 2 over n, and being multiplied 2 over n, 2 over n, and there's a reason why they do something like 2 over n, because what we're going to see when we start working with these and finding areas, there's typically going to be a something over n. We'll get into that more, but that's why they used it here. So I'm going to pull that outside of my multiplier here, and then there isn't really a we see that we're changing. It goes from 2 over n, and then 4 over n, and 6 over n. But then the last one, up here we knew that it ended at 15. We could see that. But in this one, it just says 2 times n. And so there isn't a specific number. It's going to be just n that we'll say as our upper bound. But so we're going to start, typically you start I equals 1 on the bottom as the first term. And then in this case, we end at n, because that's, so I'm looking at the pattern changing here. It's 2, 4, 6, to 2 times n. We just know that it's always being multiplied, 2 times 1, 2 times 2, 2 times 3, all the way up to n, whatever n is when we're done. Okay, so then my pattern here, we can see that it's always 1 minus something, but it's 1 minus, and it's always 2 times something. So this is, since we're using an I there, we're going to say 2i over n, and then it's always minus 1, and then it's always squared. Okay, and that's how we would, we'd represent this, summation right here. So 2 over n is always a multiplier. I take that out. You always have 1 minus, and then what's changing here? It's 2 times I. I is 1, I is 2, I is 3. So 2 times I over n, and then squared stays the same. Okay, I was just getting used to using a little bit of sigma notation. Okay, we are going to get a little introduction into, and this is kind of the main part of what we want to accomplish here is doing some upper and lower sums with some right side endpoint rectangles and left side endpoint rectangles. Okay, so the idea here, so it says, suppose we wanted to compute an area of a circle much like the ancient Greeks wanted to do a few thousand years ago. However, we do not have the actual formula. We know that the area of a circle is pi r squared, but they didn't know that, and they had to figure that out. So what the idea here is that taking some regular polygons and creating more and more sides on those regular polygons. And hopefully what you're noticing is that, and they have triangles in there. They were real familiar with triangles, the Greeks were. So that's what they started with. And you're just noticing, in a regular polygon, the more sides you have, the more, interior triangles you can draw, congruent interior triangles you can draw there. And they could approximate the area of a circle that way. So it says, using the fact that we do have a formula for computing the area of a triangle, which of these two shapes would give us the more accurate representation of the area of the circle, and why? Well, and I'm not going to calculate these out, but clearly I think you could probably see that circle 2 is going to give us a more accurate area of our circle, because the more triangles we draw in there, the more closely this polygon approximates the actual circle. Here you can see that there's more, this is our amount of error, right? Right in here, this space that's in here and here and here. That's the amount of error, and we're, it looks like we're gonna underestimate the actual area of the triangle because we have that space. But when you look at this one, well, that becomes a lot less. Those little gaps in there are a lot smaller. Okay, so it appears to me that the more sides you have on your polygon, or the more triangles you can draw, interior triangles you can draw inside of there, the closer you're going to get to approximating the actual area. Okay, so I think that's what we would say there. We would say circle 2 is a better approximation, because the number of n triangles, as the number of n triangles, I'll write this out, because as the number of triangles, let's say triangles, increases, then I can say that the area of the inscribed polygon becomes closer to the area of the circle. The area of the inscribed polygon becomes closer to the area of the circle. I'm just going to say approaches the area of the circle. Okay? So that's what we're seeing happening as we increase the number of inscribed triangles. We can see that we're getting closer to the area of the actual circle. Okay, so just an example there. Now, this would look more like some problems that you would see, in this course. So it says consider the function. So what we have here is just a parabola that's opening downward. All right, so negative x squared plus 5, and we're really only looking at it on the interval from 0, from 0 to 2. So that's the actual closed interval that we're looking at here. And so even though it looks like there's 5 tick marks on here, you do have to pay attention to what it is that they're talking about here, 0 to 2. So we're actually ending at 2 right here. So let's just keep that in mind. I'm going to put a 2 there. It says find 2 approximations of the area lying between f of x equals negative x squared plus 5, the x-axis, and x equals 0 and x equals 2. So what they're saying is, okay, so it's bounded by this parabola, that's this, the x-axis, so it's there going down to here, and then x equals 0 and x equals 2. Okay, so those are our bounds. So as I draw the rectangles in, we'll see that. So it's just basically, it's this area in here. Okay, now it says to draw in representative rectangles for each approximation. Now, what they mean by representative rectangles, and that's an important term, phrase right there, because you're going to use that a lot. Right side endpoints and left side endpoints. That's also very important, because one of these will be, an overestimate, one will be an underestimate, and that's what they mean by upper and lower sums right here. One's an underestimate, one's an overestimate. Now, it depends on whether the function is increasing or decreasing, if the right or left side are underestimates or overestimates, okay? And we'll see that here. Now, when they say a right side endpoint rectangle, okay, what that really means is you're going to start drawing, you're going to draw 5 of them. That's why they have this, you have the 5 tick marks there, because that's for how we're going to draw our 5 rectangles in there. So if they say a right side endpoint, that means that the right side of your rectangle, which is this side, is the one that should go up to the function and determine the height of that rectangle. So wherever it hits that function, so because we're decreasing here, you know, my rectangle isn't going to go all the way up to 5 here where it intersects the y-axis. It's only going to go up to, and I have to kind of approximate this, but it's only going to go to where it, you know, directly above that first partition that I have there. It's going to hit the function there and then go directly horizontally over from there. Okay. Similarly with my next rectangle, I'm going to go straight up, and obviously we're kind of just eyeballing this the best we can, but we're going to go straight up to where I intersect the function and then straight over like this. And these are going to be my, you know, my areas that I'm going to calculate. Areas of rectangles are real easy to calculate. So, and obviously I can see that with only drawing 5 rectangles in there, this isn't going to be a super accurate estimation of the area under the curve, but this is introducing us to, you know, really what we're doing for using integration to find area under a curve. So if I were to add up the areas of these rectangles that I've drawn in here, and these are right side endpoint rectangles, so hopefully you understand right side meaning that it's, you know, it's the right side of, oops, each of these rectangles that is intersecting the function, and then we're going directly over. Okay, so that's going to give me a certain, you know, approximation of that area. We know it's going to be off, and hopefully you can look at this and say, yeah, if I add those areas up, it's going to be less than the actual area under the curve because I have all these little spaces that are in there that aren't being accounted for, but that's what we're going to do to approximate it for now. Okay, now when I'm going to draw these left side endpoint rectangles, okay, so that means that actually the left side of the rectangle, so I'm going to start right on the y-axis, that goes all the way to where that intersects the function, and then I'm going to go straight over and then drop the right side down. Okay, so left side here up to where it hits the function and then over to the next partition width. And so hopefully now you can see, okay, these left sides are intersecting, creating, you know, an approximation that's going to be an overestimate of the actual area. So this would be the way I would draw, oops, this would be how I would draw my left side endpoint rectangles. Okay, so hopefully that makes sense. The left side of, you know, the height of the rectangle is touching the function and then going directly over. Okay, so that's how I'm going to draw those in. Now I'm going to run through how we're going to do a little bit of notation on finding the area here. So when we do an area on this, okay, I know that, you know, you could probably go through and calculate, but I want to be a little bit careful with notation here because this is going to lead us into kind of this limit definition of our integration. Okay, so what's important to note here, okay, 0 to 2, that's what we're working with here, but we're using 5 sub intervals, and that's why that was partitioned off in 5 pieces. And so the width of our rectangles, this is going to be a very common formula, so I'm going to write this down. The width is always calculated. Now remember, when we do an interval, we say it's an interval from A to B. Those are very commonly used letters to represent a closed interval, okay, A to B. So our formula for finding the width of each one of your rectangles is going to be B minus A. So that's, you know, in this case, 2 minus 0, so that's 2 for the total distance here. And then we're going to divide by however many partitions they ask for. And in here they said using 5 sub-intervals, right? So it said, sorry, I kind of wrote over that, using 5 sub-intervals right there. So that's, and they use, you know, n for that. So it's b minus a over n. So in this case, I would have, that would be 2 minus 0 over 5, okay? So the width of each one of my rectangles is equal to 2/5 of a unit, right? Each one of these widths is 2/5 of a unit, 2/5 plus, you know, and I could think, you know, if I mark these off, this would be 2/5, this would be 4/5, this would be 6/5, this would be 8/5, and then I would end at 2 or 10/5 right there. Okay, so just, you know, just my markings on my x-axis, that's the way that would go if I'm following what they're asking me to do. Okay, now if I were to want to find this area, I have a common width of 2/5, right? So it's width times height, and then we're just going to add all of those together, right? So I've got 2/5 times whatever this y coordinate is on this function, right? And how do I represent that? Well, it's the function value. So I would say f of 2/5 would be my first height right here, right? Whatever the function value is at 2/5, I call that f of 2/5. Okay, and then I'm going to add to that f of the next height, which is f of 4/5 right there. Okay, f of 4/5 plus f of next one, 6/5 plus f of 8/5 plus f of 2. Okay, so this is kind of the way I want to represent that. And I know maybe it looks a little confusing, but you know what we're really doing to get these heights of each of these rectangles is we're plugging these x coordinates into our function to get those. All right. Now, if you were going to go through and do this by hand, it would probably be helpful because it's kind of a repeated function you're continuing to use. I mean, you can just type those into this. It's not like a real complicated function, I guess. But what you can do is, you know, with your calculator, I would just go into my y equals right here, and I would put that function, negative x squared plus 5, into the y equals. And then if you go back to your home screen, there's this shortcut button that I think it's really helpful to use, this alpha. If you hit alpha and then the F4, then you can just grab that function. You can hit enter, and then I can say, okay, first thing I want to put in is f of 2/5. So in that function, I want to put 2/5. I'm going to do the decimal version, which is 0.4. So f of 0.4, and then I would hit enter on that, and I can see that that's 4.84. Okay, and then I could continue on alpha F4. That y1, and then I can do my next one, which is 4/5, which is 0.8. So I can type in a 0.8. Y sub 1 of 0.8 is 4.36, and then I'm just going to add up each of those function values that way. So first one, so it was, oops, so I've got 2/5. Come on, 2/5 here on the outside, and then I had this, you know, f of 2/5. We said was 4.84. F of 4/5 was 4.36, and I already worked the rest of these out. F of 6/5, if I were to plug in 6/5 or 1.2, I'd get 3.56. F of 8/5 was 2.44, and F of 2 is just 1. And if I add all of those together and multiply by 2/5, I get an approximation of 6.48. And we're going to call this one, this is our lower sum. The reason they say lower sum because it's an underestimate. Okay, so this is our lower sum. Okay, and so that's found by adding up the areas of each of these rectangles that are drawn with the right side of the rectangle up to the function. Okay, so that's our lower sum in that case. All right, now in a similar way over here with my right side rectangles, I kind of wrote a little too big there, but let's see if we can squeeze this in. So if I were to do this one, it's going to be a similar process. So it's going to be 2/5, but in this case, you know, I'm actually starting with my first function value is found at 0 because that's where my first height of my, I'm doing left side rectangles. It's actually f of 0 to get this first height. So that's going to be f of 0 plus f of, well, the first one, which is 2/5. Okay, so that's this one right here, right? 2/5, 4/5, 6/5, and 8/5. And that's actually where I'm going to stop then is f of 8/5, and that's going to be my, my last rectangle. That'll be 5 of them, right? Because I'm not doing f of 2 for a height because, that's not the height there. The height is on the left side, right? And that's why I have to, they're kind of staggered, right? In this one, I went from 2/5 to 2, so 2/5 to 2 there. But in this one, I'm actually starting at 0. I'm starting with my first height at 0 right there, and then 2/5, 4/5, 6/5, 8/5, and that's actually where that's my last height, right, of my last rectangle is at 8/5, so that's why I'm going to stop there. And then f of 4/5, f of 6/5, and the last one is f of 8/5. Okay, so I'm just going to total all of those up, so that's just going to be area, and then it's going to be 2/5, and if I've already kind of calculated these out, right? F of 0 in this case is just 5, so I have 5 plus the 4.84, and these are going to kind of be the same, plus 4.36 plus 3.56 plus 2.44, and that would be my last one, right? That's 5 numbers, 1, 2, 3, 4, and 5. And then I'm going to add those and multiply by 2/5, and I would get an area that's equal to 8.08, and that would be called my upper sum, because it's an overestimate. Okay, so we have, that's a good introduction to, what we're asking you to do on a lot of these problems is finding an upper sum and a lower sum. And it doesn't always mean that right side is going to be a lower sum and that left side is going to be an upper sum. It just depends on if the function's decreasing or if it's increasing. If it was an increasing function, these would actually be, your right side would end up being an overestimate, and the left side would be an underestimate. But we'll take a look at that more in detail. But for right now, that'll be all I do for this video piece of the notes, and I'll continue on in the next video.